All right, good afternoon. In this video, we'll start working on section 6.1. It'll probably take a couple of videos to get through this, but let's go ahead and get started. As always, when we're starting a chapter, it's a good idea to look ahead and see what it is that we're getting into. And chapter 6 is on normal probability distributions. There's a total of 6 sections in the chapter, 6.1 through 6.6. Like I said, we'll be doing 6.1. This will take us a couple of days. Basically, normal distributions, we'll be looking at basically the bell curve that led us to the empirical rule, the 68, 95, 99.7% rule. Section 6.1 introduces it and how to use what's called a standard normal table. 6.2 will be basically story problems or applications of this normal distribution. And then the rest of it from here gets a little bit more specific. We'll deal with section 6.3 and 6.4 when the time comes. Section 6.5 is about how do you tell if a distribution you have is normal or pretty close to normal. And then finally, section 6.6, we'll see how we can use the normal distribution to approximate the binomial distribution that we studied in chapter 5. So chapter 5 focused on discrete distributions. Chapter 6 focuses on continuous distributions. We'll spend a little time talking about what's called the uniform distribution and also a little time talking about the normal distribution, probably a lot of time talking about the normal distribution. So this will look somewhat familiar. If you have a continuous random variable and the distribution is symmetric and bell-shaped, as shown in the picture at the bottom of your screen, then it can be described by the equation shown here in Formula 1. So that's a pretty intimidating looking equation. It's defined in terms of the natural exponential we saw in the Poisson distribution. It's a function of both mu and sigma, and also, as you can see, there's a pi in it. So there's a pretty complicated equation. If it turns out that the mu is 0 and the sigma is 1, which is pretty much as simple as you can get, you still end up with a pretty complicated equation. For that reason, we'll end up doing a lot of work with the normal distribution using a table rather than direct calculation. So I've sent you a copy of the table in your email, so you should try to print that if you can. If not, at least just keep the PDF copy of it handy as we work through all of this. So a key idea that we'll need when we work in section 6.1 and beyond is that the probability of an event can be related to an area. So to see this, we're going to look at this probability distribution. If we have 3 births, we want to consider the number of girls in 3 births. We've written out the sample space for this quite a few. If we have 3 births, then what's possible? Could be all 3 girls, a girl, and a boy, a girl, a boy, and a girl, and then finally a girl and 2 boys. Then I'll repeat this over again with the first column being B's. After you've done this a few times, you get used to the pattern. All right, so then we're going to consider what is possible as far as number of girls. So you can see by taking a look at this first histogram that the probability of getting no girls, there was a 1/8 chance of that occurring. The probability of getting 3 girls, there was a 1/8 chance of that occurring. And then the other 2 possible outcomes, that of getting 1 or 2 girls, each had a 3/8 probability. So now, taking a look at the 2 histograms to the right, the probability of getting 3 girls, we saw that that has a probability of 1/8. And if you think about it, if we draw this histogram, I'm making it so that the bar there has a width of 1, and the height of the bar is 1/8. And as you know, the area of a rectangle is the height times the width. So here it is 1/8 times 1, or 1/8, of course. So that area of that little rectangle can be associated with the corresponding probability. As another example, if we wanted to know the probability of having fewer than 2 girls, well, fewer than 2 girls would be either 0 girl or 1 girl. So that would be the area shown here in yellow, which is actually half the distribution. So We can see that this is going to be 1/8. That's going to be 1/8 plus 3/8, which is 4/8, which of course is 1/2. Again, the big idea is that the area can be seen as corresponding to the probability. Okay. As another example, we're going to consider what happens when you roll 2 dice. If you roll 2 dice, each die has 6 possible outcomes. So for the first die, it could be anything from 1 through 6. For the second die, it can be anything from 1 through 6. And so this gives us a total of 6 times 6, or 36 possibilities, ranging from 1 on both dice, which would give you a sum of 2, to 6 on both dice, which would give you a sum of 12. So then there's 36 possibilities. For the first one, we would like to know what's the probability of rolling a 4. Out of the 36 possible outcomes, there's 1, 2, 3 ways of getting a 4, and 4/36 is 1/9. The probability there is going to be 1/9. Again, taking a look at the histogram shown here in blue to your right, across the horizontal axis, we have the different values of our random variable. We're interested in getting an outcome of 4, and then the height of the bar is a little bit higher than 0.08. 1/9 is, how big is a ninth? A ninth as a decimal is about 0.11, and so that should end it up a little bit higher. All right, so we'll have to take a look at that. For the probability of getting 10 or higher, 10 or higher would be 10, 11, or 12. There's 3, 5, or 6 out of the 36 possible outcomes, and that works out to 1/6. Again, the important takeaway right here is that if we take each of these bars to have a width of 1, then using the area formula for a rectangle, the area is height times width. So if the width is 1, then we can associate the area with the under the top of the bar with the corresponding probability. All right, so then once again, the probability can be associated with the area under a curve. For a discrete distribution, the histogram is made up of individual bars. For a continuous distribution, what we can think of as the histogram is made up of infinitely many, infinitely thin bars. So we'll be working next, we're actually starting 6.1 now. We'll be looking first at a uniform distribution and then the normal distribution. So for a uniform distribution, the area under the graph of any continuous distribution is going to be equal to 1. Since there's a correspondence between area and probability, probabilities can be found by finding corresponding areas under the graph using a rectangle area formula. So what a uniform distribution is like, if you think about what the word uniform means, it means something is the same. So what's the same is the probability is constant for all possible outcomes. So a continuous random variable has a uniform distribution if its values are spread evenly over the range of possibilities. The graph of a uniform distribution results in a rectangular shape, as shown in the picture here in kind of a light blue color. Suppose that we have the function f of x equal to 1/4 that has domains 0 through 4. The area under the curve is 1. Taking a look at the blue bar down below, its height is 1/4 and its width is 4. 1/4 times 4 is 1. And then all the values are positive and each under 1. And so it is the graph of a distribution. There's a correspondence between probabilities and areas under the curve. So if we want to know the probability of getting an x value that is larger than 2, that would correspond to this rectangle, larger than 2, right? So that has going to be probability 1/2. for a probability of less than 1 would be this amount, that is going to be 1/4, right? So that probability is 1/4. The probability of getting one value exactly is going to be equal to 0. And the reason for that is that if we're taking x to be exactly equal to a particular value, then the width of that rectangle is going to be 0. The graph of a continuous probability distribution is called a density curve. In a density curve, the total area under the curve has to equal 1, and every point on the curve must be above the x-axis. That is, the function values are positive. And I didn't write it here, but additionally, they have to be less than 1. Okay, so we talked about the normal distribution back in chapter 3. This next part has to do with what's called the standard normal distribution. The shape of a bell curve or normal distribution depends on the mean and also the standard deviation. So in the graph shown here, you can see there's 4 different normal distributions graphed for different means and standard deviations. They're all given using this formula, which we saw at the start of the chapter. That formula, like I said, usually is too difficult to work with, so we'll end up using a table or a computer. The graph shown to the right, 3 of the graphs have a mean of 0. And you'll notice that the peak on each graph is centered right at 0. The graph of the green distribution is centered at -2. For the 3 graphs centered at 0, they have different variances. The one for the kind of orange one has a sigma squared of 5. That should look pretty spread out to you. The one that has a sigma squared of 0.2, that is not very spread out at all. Most of the values are clustered between -1 and 1. So a distribution, and a normal distribution, is determined by what its mean looks like and also what the standard deviation or variance is. Because we can't go around with a table for every possible normal distribution there is, typically what we do is we apply a transformation to our particular distribution and end up working with what's called the standard normal distribution. What the standard normal distribution is a normal distribution that has a mu of 0 and a sigma of 1. So out of all these different normal distributions you can have, we're going to pay special attention to the one where the mean is 0 and the sigma is 1. Of course, the area under the curve is going to equal 1, but this is basically a picture of our standard normal distribution. It's going to be centered at 0. Its standard deviation is going to be 1. One of the main things that we're going to want to do is to be able to find probabilities when given what are called z-scores. So we need to talk about what a z-score is. So we had dealt with a z-score back in chapter 3, but we should go back and take a look at that. The z-score is basically a measure of the number of standard deviations a particular data value is from the mean. We saw this formula in chapter 3, that z is equal to x minus mu over sigma. X minus mu is the deviation from the mean, and it's put into units of standard deviations. So when you draw the standard normal distribution across the horizontal axis will be z-scores. It's centered at 0, of course, because the mean was 0. And then we'll have 1, 2, or 3 standard deviations to the right, and then 1, 2, or 3 standard deviations to the left. So one of the main things we want to be able to do is to turn a z-score into a probability. So there's different types of standard normal tables in use. The one that we have is called a cumulative distribution. There's also a 0 to z table that some books use. Our book measures the areas starting at -infinity and going up to a positive value of z. And how to read the table. The boundaries of the table make up a value of z along the outside, and what's inside is going to be the probabilities. So easiest way to see how this works is by trying it. Let's say that we want to find a probability corresponding to a z value that is less than 1.34. It's always a good idea, especially if you're just starting out, to draw out the normal distribution you're working with and also locate the area that you want. We wanted to know for a z of 1.34, what is the area to the left of 1.34, because it says z is less than 1.34. So referring to our z table, it says 1.34. Looking along the left side of the table, 1.3 is right here. The left side or left margin of the table gives the whole number and then the tenths place for the value of z. So 1.3 is here. And then the columns across are for different places or values of the hundredths place. Since we wanted 1.34, we're going to go to the 0.04 column. And where those two intersect, we're going to find our probability value. So 0.90988 will be the probability. All right, so that takes some getting used to, so we're definitely going to practice it. Like I said, if you have your own z table handy, you'll want to definitely try this on your own. For the next one, we wanted a z less than 0.67. Okay, so the distribution is centered at 0. We wanted 0.67. So locating the table, there's no whole numbers here. So it's only going to be the tenths place, which is 0.6, and then the hundredths place, which is 0.07. So 0.67. So where that row and column intersect, 0.74857. And that's the probability. For the next one, we want the probability corresponding to a z that is greater than -1. So let's try that. Again, definitely a good idea to make a picture. This time we wanted the z greater than -1. So the distribution is centered at 0. And we're looking for the right of -1. Okay, so the thing is that our z table tells us the area from -infinity up to a positive z, right? So we need to kind of translate that to our specific situation that we have here. So we have a 1 in our table, 1.0. That will have area 0.84134. Okay, and that is the area to the left of a z of 1. So how much area is under the curve altogether? Well, the area under the whole curve is going to be 1. So if we take 1 minus that 0.84134, what's left is 0.15866. That's the area to the right of this 1. The distribution, remember, is centered at 0, and it's symmetric across that mean. So if 0.15866 is to the right of positive 1, then that same amount, 0.15866, will be to the left of negative 1. So our final answer here is 0.15866. Okay, an important thing to remember here is that this is a probability, right? And remember that probability is always greater than or equal to 0. All of the numbers in the body of our Z table are probabilities, so they're positive. So even though we're finding the probability less than a negative here, our area is never going to be negative. So if you were thinking it should be negative 0.15866, then that's incorrect. It needs to be a positive value. Okay, so that will be the end of this video. We're going to try some more examples in the next video.